We now come to the crucial property that the real numbers possess, that rational numbers do not. First of all, note that our axioms so far do not preclude the possibility of holes, do not seem to get rid of the holes. So far, the field axioms and the order axioms very much allow Q. Q is an ordered field. The only thing we have seen is that every ordered field also contains a copy of Q. Now the question arises, what is the crucial property that Q is lacking that makes the appearance of these holes? What we need is the axiom of completeness. This axiom of completeness plugs all the holes, as we shall see. Now this is the central point of real analysis. What I am about to do now is what is the key that allows us to define limits and continuity and so on in a satisfactory manner. Because of the central nature of this axiom, we shall present multiple versions of it. We shall spend some time on this, and even in a later chapter on sequence and series, we'll visit this yet again. So, the most common way to state the axiom of completeness is through the least upper bound property. I wouldn't say this is the simplest way to do it, but this is the most common way. And to do that, we need some definitions. Definition. This is the definition of bounded above. Let F be an ordered field. F be an ordered field. And S some subset of F. Okay. We say that S is bounded above if there is some B in F such that for all S in this set S is less than or equal to B. Okay. So there is some element in the field that dominates every single element from the set S. In that event, we say that the set S is bounded above. Now the crucial definition is of least upper bound and completeness, which is, as I have emphasized several times already in this short span, the central point, the central key axiom that makes analysis possible. Again, let F be an ordered field. And S a subset of F. Okay. Assume that S is bounded above. A least upper bound or supremum of S, this is usually denoted sup of S, okay, is an element S in F. Note, the element S must come from F. So let me just not use S, let me just use U for upper. It's an element U in F such that property 1, U is an upper bound for S? Well, that's seemingly straightforward because we are trying to define what a least upper bound is. The very least it can be is that it's an upper bound. Property 2 is the crucial property. What it says this is if B is any upper bound for S, then B is greater than or equal to U. In other words, this U is the least upper bound, as the definition was trying to tell. We say that F is complete if every set that is bounded above has a supremum, or least upper bound has a supremum. Okay, that's a long definition. Let's see some examples to clarify what is going on. Examples. Consider the set 1, half, 1/3, 1/4, so on. Consider this set. Is this set bounded above? Yes, this set is bounded above. What's a good upper bound for this set? 1 is an upper bound. 1 is an upper bound. Note, I haven't told you where this set is, so let me just take it as a subset of Q. In fact, 1 will be the least upper bound of this set. Why is that the case? Well, suppose B in Q is any upper bound, B has to be greater than or equal to 1 simply because 1 is present in this set. For this reason, the second property, if B is any upper bound for S, then B has got to be greater than or equal to U, is trivially satisfied. So supremum, if you call this set S, supremum of S is just 1. Okay. Let's see another example. It's a slight variant of this example. I define S to be, instead of 1/2, 1/3, so on, I'll define it as half, 2/3, 3/4, 4/5, and so on. This is just 1 minus 1 by n, such that n is in n and n greater than 1. Okay, it's a collection of all numbers. Again, I will take this as a subset of Q. It's a collection of all numbers, half, 2/3, 3/4, 4/5, so on. Essentially 1 minus 1 by n. Now, what is the upper bound? What is an upper bound for this set? And does it really have a least upper bound? Well, let's see that. Notice that 1 is an upper bound. Notice that 1 is an upper bound. That's clear because all elements are of the form 1 minus 1 by n. Claim is that 1 is actually the supremum. 1 is actually the supremum. Well, let's try to argue as follows. Suppose B is in Q and B is an upper bound for the set S. Okay, if B is strictly less than 1, we need to reach a contradiction. If B is less than 1, then 1 minus B is in fact greater than 0. In fact, we can assume that this B is greater than 0 because b has got to be an upper bound. So you have 0 less than b less than 1. 1 minus b is greater than 0. We have to reach a contradiction somehow. Now, I will use one fact that I leave it to you to check. There is n naught in n such that 1 by n naught is less than 1 minus b. Okay? This is in fact known as the Archimedean property of the rational numbers. It's a consequence of the Archimedean property. We will see that in a few modules. However, to prove this is not at all hard for the rational numbers, so I urge you to try it right now. Okay? So check that you can find n naught in n such that 1 by n naught is less than 1 minus b. Okay? Therefore, 1 minus 1 by n naught will be greater than 1 minus 1 by b, 1 minus 1 minus b, which is in fact equal to b. Okay? So, we have an element, this is an element in S, this is an element in the set S that is greater than b, so b cannot be an upper bound. B cannot be an upper bound. So this proves that 1 is the least upper bound of the set S. Okay, so that's enough for the examples right now. Before we proceed with some more theorems, I want to first make some remarks about infimum. Rather, I'll just put it as an exercise for you to think about. Define lower bound in an ordered field. In an ordered field, and greatest lower bound. This is also called the infimum. Infimum, and that is denoted infimum of S. So define lower bound and greatest lower bound in an ordered field. Show that an ordered field is complete if and only if any set that is bounded below has a greatest lower bound. Okay. So do this exercise. You will have to define what lower bound is. You have to define what bounded below is. You will have to define what infimum is. Show that completeness is same. You can reformulate completeness in terms of lower bounds instead of upper bounds. Now the definition of completeness seems very hard. It says that a field is complete if every set that is bounded above has a supremum or every set that is bounded below has an infimum. The reason is that any definition in mathematics that was arrived at after many years of work has this tendency to be a bit opaque, because the distance between what motivated the impetus for studying for figuring out a proper definition and the final definition coming about is many years. Because of that, it's not really clear what is happening. So what we will do is, we will now prove two more intuitive properties that complete ordered fields will possess, called the Archimedean property and the nested intervals property. These two properties are more intuitive from our understanding of what a straight line's behavior is supposed to be. Before we get to these two results, let us first see a useful characterization of the supremum that will be of immense benefit to us in these proofs. Proposition, this is characterization of the supremum. This result says the following. Let F be an ordered field, S subset of F bounded above. Let U be supremum of S. Then for each fixed positive epsilon coming from the field, we can find an element S in S such that U minus epsilon is less than S is less than or equal to U. Call this equation star. Conversely, assume that U is an upper bound for S that satisfies star. Then U is supremum of S. So this gives a complete characterization of the supremum. What this proposition says is the following. You have a set S in an ordered field that is bounded above. The supremum also exists, which we are denoting by U. What it says is if you knock out a small portion of the supremum, that's essentially what subtracting by a positive epsilon means, then that ceases to be an upper bound of the set. There will be some element S that is greater than U minus epsilon and less than or equal to U. Okay? Needless to say, this choice of this element S depends on the choice of epsilon. If you choose a much smaller epsilon, you will have to modify this element S in all probability. Okay? Proof. The proof is a proof by contradiction. We had already seen one or two proofs by contradiction, specifically the irrationality of root 2. The essential idea is that we will assume that what we are trying to prove is false and add it to the list of hypotheses that we have. Then we can play around with the given hypothesis along with our new assumption and reach a contradiction. Then by the law of excluded middle, our assumption must be false. This technique is really powerful, especially when we don't know how to start a proof. You have a theorem, you don't know how to prove it. Just add the negation of what you want to prove as a hypothesis, as an assumption, and proceed. So assume. So first we will prove the first part, not the converse. Assume that for some choice of epsilon, greater than 0, star is false. Then we have U minus epsilon is greater than or equal to S for all S in the set S, right? Our star says we can find some element S that satisfies the inequality U minus epsilon less than S less than or equal to U. The negation of this statement is that for some choice of epsilon greater than 0 and all choices of S, U minus epsilon is greater than or equal to S. Check that this is the correct negation. This is the correct negation. Okay? But U minus epsilon is less than U. Why? Because epsilon is positive. U minus epsilon is less than U, which contradicts property 2 of the supremum. You cannot have You cannot have an upper bound. U minus epsilon is going to be an upper bound. You cannot have an upper bound that is strictly smaller than the least upper bound. So this contradiction shows that the supremum will necessarily have property star. On the other hand, suppose set S is bounded above, and U is an upper bound, that satisfies star. Then we have to show that S is supremum of, not S, U is supremum of S. Okay. How does one show this? Well, let B be any upper bound for the set S. Okay. Now suppose B is strictly less than U. Then U minus B, set this to be epsilon. Okay. Then set epsilon to be U minus B. This is greater than 0 because U is greater than B. Now, because of the property star, we are now assuming that star is satisfied. We can find S in S such that U minus epsilon is less than S is less than or equal to U. This is simply property star. But U minus epsilon is actually U minus B. This is less than S, this is less than or equal to U, or in other words, B is less than S, is less than or equal to U. Okay, so B cannot be an upper bound. Okay, hence we must have U to be supremum of S. So this completes the proof. Now what we will do is we will proceed and prove the nested intervals theorem and the Archimedean property in the next module. This is a course on real analysis and you have just watched the module on completeness.